And now for the next topic for today, we are going to start looking at algorithms. And I'm going to start you off with this.
What's an algorithm? In computer science, an algorithm is a set of instructions for solving some problem, step by step. Typically, algorithms are executed by computers, but we humans have algorithms as well. For instance, how would you go about counting the number of people in a room? Well, if you're like me, you'd probably point at each person, one at a time, and count up from 0. 1, 2, 3, 4, and so forth. Well, that's an algorithm. In fact, let's try to express it a bit more formally in pseudocode, English-like syntax that resembles a programming language. Let n equal 0. For each person in room, set n equal to n plus 1. How to interpret this pseudocode? Well, line 1 declares, so to speak, a variable called n and initializes its value to 0. This just means that at the beginning of our algorithm, the thing with which we're counting has a value of 0. After all, before we start counting, we haven't counted anything yet. Calling this variable n is just a convention. I could have called it most anything. Now, line 2 demarks the start of a loop, a sequence of steps that will repeat some number of times. So in our example, the step we're taking is counting people in the room. Beneath line 2 is line 3, which describes exactly how we'll go about counting. The indentation implies that it's line 3 that will repeat. So what the pseudocode is saying is that after starting at 0, for each person in the room, we'll increase n by 1. Now, is this algorithm correct? Well, let's bang on it a bit. Does it work if there are 2 people in the room? Let's see. In line 1, we initialize n to 0. For each of these 2 people, we then increment n by 1. So on the first trip through the loop, we update n from 0 to 1. On the second trip through that same loop, we update n from 1 to 2. And so, by this algorithm's end, n is 2, which indeed matches the number of people in the room. So far, so good. How about a corner case, though? Suppose that there are 0 people in the room, besides me, who's doing the counting. In line 1, we again initialize n to 0. This time, though, line 3 doesn't execute at all, since there isn't a person in the room, and so n remains 0, which indeed matches the number of people in the room. Pretty simple, right? But counting people one at a time is pretty inefficient too, no? Surely we can do better. Why not count 2 people at a time? Instead of counting 1, 2, 3, 4, 5, 6, 7, 8, and so forth, why not count 2, 4, 6, 8, and so on? It even sounds faster, and it surely is. Let's express this optimization in pseudocode. Let n equal 0. For each pair of people in room, set n equal to n plus 2. Pretty simple change, right? Rather than count people one at a time, we instead count them 2 at a time. This algorithm does twice as fast as the last. But is it correct? Let's see. Does it work if there are 2 people in the room? In line 1, we initialize n to 0. For that one pair of people, we then increment n by 2. And so by this algorithm's end, n is 2, which indeed matches the number of people in the room. Suppose next that there are 0 people in the room. In line 1, we initialize n to 0. As before, line 3 doesn't execute at all, since there aren't any pairs of people in the room, and so n remains 0, which indeed matches the number of people in the room. But what if there are 3 people in the room? How does this algorithm fare? Let's see. In line 1, we initialize n to 0. For a pair of those people, we then increment n by 2, but then what? There isn't another full pair of people in the room, so line 2 no longer applies. And so by this algorithm's end, n is still 2, which isn't correct. Indeed, this algorithm is said to be buggy because it has a mistake. Let's redress with some new pseudocode. Let n equal 0. For each pair of people in room, set n equal to n plus 2. If one person remains unpaired, set n equal to n plus 1. To solve this particular problem, we've introduced in line 4 a condition, otherwise known as a branch, that only executes if there's one person we could not pair with another. And so now, whether there's 1 or 3 or any odd number of people in the room, this algorithm will now count them. Can we do even better? Well, we could count in 3s or 4s or even 5s and 10s, but beyond that it's going to get a little bit difficult to point. At the end of the day, whether executed by computers or humans, algorithms are just a set of instructions with which to solve problems. These were just 3. What problem would you solve with an algorithm? What's an algorithm?
Oh, it
In
looks
computer
like it's
science,
repeating.
an algorithm.
Oh, there we go. Now I'm in the next slide. Now here I'd like you to take a moment and think about your experiences so far programming. What makes two pieces of code the same? And can there ever be two pieces of code that you would consider to be the same, even if they were not identical? And Nathan, can you expand on your comment about the carrot algorithm? Why would you consider it the same? All right, I am not going to give you an answer to this because I want you to discover the answer. Now, I would like you as a class, actually, this is but part of it. I'd like you to head over to the Google Classroom and in Brightspace. Oh, it didn't get posted. Let me post this. There we go. Let me reload. I would like you to head over to Google Classroom, and do you see Tuesday afternoon in-class task? Click on that and grab yourself the document that goes with it. Now you'll see that I've taken the slides and put them in here. So what I'd like you to do now as a class is to determine, to get an answer to these problems. So find a person in the class whose birthday is before yours, find a person whose birthday is after yours, and so on. So there's 10 problems. I'd like you all to do this. Keep track of it in your own document. That's why I posted it in the Google Classroom. And yes, so we'll take a few minutes to do this. If you could, you can certainly use the chat to achieve this. All right, so I have been looking at your documents and you have been making progress in terms of solving these particular questions. Now, let me continue. So there were a number of problems in here for you to solve. And some of them were easier than others. For instance, find a person whose birthday is before yours. That's pretty straightforward. The same with after yours. Number 3 and 4, find a person whose birthday is the closest before and after yours. Yeah, okay. Number 5, ditto. It's reasonably straightforward. Number 6, find the person with an equal number of birthdays before and after. Much more involved. Find 2 people with the closest birthdays in the room. That's more involved. Find the shortest period of time in which 3 people have birthdays. Again, same with number 9 and number 10. These are all far more involved questions. So let's take a look at how they looked. So problems 1 and 2 were similar. As soon as you found one person who met the criteria, you're finished. If you have 3 and 4 as your problems, that meant you need to talk to every other student to be able to answer it, but you only needed to keep track of the closest birthday. So again, a straightforward problem, but one that required you to talk to everyone. Number 5 was equally simple to solve as soon as you'd completed 3 and 4. Now, Here are the more involved problems. Problems 6 through 10 basically meant you had to compile every single person's birthday. You had to write them all down. If you tried the 3 problems 7 through 9, they have a very similar strategy, which meant that if you'd solved the problem for one of them, you also effectively have solved the problem for the other 2. And the 10th is a different way of looking at the previous problems. Now, which problems did you need to do something similar to solve them? That's what I summarized here for you. And we have essentially, it looks like 6 unique problem-solving strategies that come out of this. Even though there's a little bit of duplication over some of them, there are 6 distinct solutions. Now, I want you to take a moment and think after you read this slide. So take a moment, read the slide. Now in here, you'll see one sentence. Have I seen this problem before? And how is this problem similar to other problems that I've solved? These are 2 really important questions. And that's why you have many different challenges to complete in the course. And that's why I like the course the way it's laid out. It's because you do have many different problems that you need to solve. And if you're getting solutions from other people and just punching them in and that's it, you're wasting your time. Because the real value in learning computer science is practicing the problem solving. You can't copy someone else's problem and understand it. You have to solve it yourself, which is why it's so important that you try your level best to complete these problems. It's not worth banging your head against the wall nonstop and being stuck. You can certainly ask for help. There's nothing wrong with asking for help. But if the first thing you do is reach for the solution, that's going to get you nowhere. Now, if you want to think like a computer scientist, ask yourself, what is a problem? We looked at 10 of them, and we discovered that many of them are quite similar. We also discovered that if we solve the problem for one problem, we have a pretty good idea of how to solve other problems that are very much like it, which is why we're back to those 2 questions that I really like. Have I seen this problem before? And how is this problem similar to other problems that I've solved? Notice how they're not exactly the same question. Now, here is something that I'm going to give to you for homework. I would like you to think about this. You have this in a document, the one that I just shared with you, in fact. So if I were to switch to that tab, here we go. If I scroll down on this particular tab, you will see here I have the section, be sure to check out algorithm 6 on the next page. So I have a number of pictures here that I would like you to work on for your homework. So we have algorithms 1 through 6. Sorry, I was trying to stay on task. So we have algorithms 1 through 6 that I'd like you to be doing for your homework. In essence, what you're looking at here is our 6 different algorithms, and each of the algorithms tells you which way to move and which way to turn. It's directing you to move in a grid. And your goal here is to examine these algorithms and to determine which of these algorithms are in essence the same as each other and which ones aren't. So that is going to be your homework. So I think you can probably figure out from the pseudo code that you're seeing here what each one does. Now, in case you're not familiar with flow charting yet, here we have the circle for start and for end. Those denote a beginning and an ending point. If you have a rectangle, typically the rectangle is an activity. It's a task that has to happen. So the first activity we're looking at, count, is assigned the value 0. This is an initialization. And then here we have a diamond. A diamond is a decision structure. And if the count is under 4, if it's true, you move forward and you turn right and you increment count by 1. And then we loop back to the decision structure. We ask, is count less than 4? If the count is greater than or equal to 4, then it's false and we end the program. That's how a flowchart works. And you'll notice the braces here. The braces indicate a block of code that gets repeated. And you can see here, repeat 2 times. So that's like a for loop. It is a for loop. This is going to be your homework. You already have this document. Tomorrow, we will take this up. We will look at it in class. Tomorrow is our in-person learning, so I will see you at 8:45 in the morning. And I noticed a few of you tried joining me earlier on today at like 11 o'clock. So I guess maybe you were late for your other class. All right, and at this point, I will stop recording.